Assalamu alaikum. From this lecture, we are going to talk about the percentage differential protection of the three-phase transformers. So we have already discussed in detail the percentage differential scheme. Differential protection scheme. And now we are going to apply that scheme to transformers as well as bus bars. In three-phase transformers, we usually have two different type of winding connection. One is delta and the other one is Y, which is also known as star connection. Whenever we have same winding connections on primary as well as secondary side of the transformer, we do not have any phase shift between the two sides. But whenever we have a delta Y, Y delta, Y grounded, delta and delta Y grounded connections, so these four transformers will have the phase shift and the magnitude difference in the current values on primary and secondary. So as we know that in the differential scheme we have a overcurrent relay that is fed from CTs of the primary as well as secondary of the transformer. So the spill current is flowing through this relay, and the current that is in this branch is known as circulating current. So the spill current that is passing through the relay is I1 minus I2, which is actually the differential current of the two CTs. This is your CT number 1 and this is your CT number 2. So in order to get the differential current accurately, we should have the same currents on primary as well as secondary, right? That we have to compare. But in case of delta Y connections, we have a phase shift between the currents. And now we have to tackle this problem. Secondly, the voltages on both sides of the transformer is different. Either it can be a step-up transformer or it can be a step-down transformer. In both the cases, the voltages on both sides of the transformer are different. So current will be different, and therefore we have to use different CTs on the primary and secondary side of the transformer. And therefore, first we have to talk about the CT connections in the three-phase transformer measurement on the primary as well as secondary side. For example, we have a Y grounded delta transformer. This is the supply side and this is the load side. And these are the phases of the transformer. So as the primary is connected in Y, so we have two different voltages: line to line voltage, that is between the two phases AB, and line to neutral voltage, that is between the single phase and the ground, which is this common connection. In Y connection, we know that line and phase currents are same. And it can be seen from this diagram that the line current is IA, and that same current is passing through the winding as well. So the line and the phase current is same in the Y connection. But as we move towards the secondary of the transformer, the phase current is IA, but the line current is IA minus IC, because we have one current that is actually moving through this wire. So this is IA minus IC. IC. So if we have to get the current values from the primary as well as secondary side of the transformer, we are getting IA from the primary side, and for the CT of the secondary side we are getting IA minus IC, which has a phase difference of 30 degree in comparison to the primary current, that is I capital A. Right? So in order to compare these two currents, we should have the same value that has to be compared, right? So now we have to devise a solution for that. From the basic theory, we know that this IA is the primary current that is flowing through the line, and this IA, I small a, is actually the secondary phase current that is passing through the secondary winding of phase A. But the current that is coming out at the terminals of the transformer is IA minus IC, because the secondary of the transformer is connected in delta. So due to the delta connection, we are getting IA minus IC. And from the phasors, when you add IA and minus IC, you will get this phasor. That is actually under root 3 times more than IA in magnitude and lagging IA by 30 degrees. So we cannot compare this current and this current. So now we have to make CT connections in such a way that these two currents can be compared in some manner, right? So first we are going to assume a simple example in which we have CTs attached to each of the phases, and we are taking delta Y transformer. The phase currents are I capital A and I small a. I capital A is for the primary side of the transformer and I small a is for the secondary winding of the transformer. And for this case we are assuming that the turn ratio is 1:1, so that this IA will be equal to this IA. So the primary side current in the phase A of the transformer is actually equal to the secondary side current. So now there should be one current that is entering this dot. So if the current is entering this dot, then one current will be leaving this dot. We know that IA is the current that is after this node point. So there is another current that is coming from the winding C, because this is delta connected 3-phase winding. So it means this IC is moving from the C winding towards this node. So there is one IC that is coming to this point. Now the current that will be entering this node should be the combination of these two currents. So this will be IA minus IC. So this CT is actually stepping down this current or measuring this current if it is connected at this point, right? These are the terminals that are available to the CT. So you cannot measure this IA because this is actually inside the transformer. So the CT will be measuring this IA minus IC. But on the Y side, we have the phase current that is passing through this winding and the line current, both are same. So if both the currents are same, so this CT is actually measuring the current that is passing through the winding, which is actually the phase current and also the line current. So the current that is being measured by this CT is actually IA. We have a phase difference of 30 degree between these two currents. So we have to make such connections of the CT so that we should not have this 30 degree phase shift. Otherwise we will not be able to get the accurate results, right? So what we do, this is the final current depiction in the 3-phase transformer. On the delta side, the phase current is I capital A and the line current is IA minus IC. Similarly, on the Y side, we have the same phase current as well as the line current, and this same current is being measured by the CT. But this CT is actually measuring IA minus IC that we have discussed before. Now, to remove this phase shift, what we can do is we have to choose the connection of CTs in such a way that IA minus IC is being measured by CT. So the similar type of current should be measured by this CT. This side was delta connected. So what we can do, we can connect the CTs in Y connection, and on the Y side, Y grounded side, we will be connecting CTs in the delta connection. Now we know that this is IA current that is passing through this winding, and then one IC current is flowing from the C winding towards this node. So the current that is passing through this line is IA minus IC, and the same current will be measured by the CT, that is IA minus IC. And when we move down, this current will be passing through this restraining coil. So these two coils are the restraining coil, this is the operating coil, and then we have one current that is moving from this side to the CTs of the secondary of the transformer. So as the secondary of the transformer is Y connected, all these windings are Y connected. So what we have done, we have connected the CTs of the secondary side in delta. So this current IA will be measured by CT. This is the line current measured by CT, and on the secondary side we have some step down current IA, I small a, and then this current will be moving towards this node. And at this node there is one current IB that should be going through this CT. So there is the current that is moving towards the node is IB minus IA. The current that is moving towards the node, this node, is IB minus IA, right? One current is moving towards this node, one is leaving this node. So the current IB minus IA is moving towards this node, and this current is flowing through this branch. Now as IA minus IC is moving towards this node and through this part of the restraining coil, then there is another current that is IA minus IC that is passing through the other part of the restraining coil, and that is moving towards this node. And this node is linked with two CTs. One is of the phase A and the other one is of the phase C. And from phase A we have a current IA passing through the CT winding, CT secondary winding. So the current that is flowing through this wire is actually IA, and from this winding we have a current IC. So this IC current is moving towards the node. So the current that is moving towards this node from the restraining coil is actually IA minus IC, and both these currents are actually in phase, so they don't have any phase difference. So we can easily compare these two currents. Similar is the case for these two differential relays. So if these two currents are equal, then there will be no spill current that will be passing through the operating coil of the differential relay. But if it is not equal, then the relay will operate. So as a rule of thumb, by doing this whole evaluation, we came to the conclusion that if we have a delta connected side of the transformer, we will use CT in Y connection, and if the transformer side is Y connected, then the CT will be in delta connection. And by doing this, we are actually making the currents equal in magnitude as well as in phase for the comparison, because we have to pass a differential current through this operating coil, and these two currents that are passing through the restraining coil should be equal in magnitude as well as in phase. So that's why we use Y connected CTs on the delta side of the transformer and delta connected CT on the Y side of the transformer. Thank you.